Isomerism Part 2. We're going to introduce, well, we've already introduced the concept of enantiomers and diastereomers, but a more useful concept is that of chirality. You like those root words? Chiral is a Greek root, which means hand. So it's handedness. So if the molecule has a chiral center, then it's possible to rearrange the connectivity around that carbon so that you get a different arrangement. That's essentially what chiral means. So here's our list again, and we're gonna introduce enantiomers and diastereomers. And there's a practical experimental difference here in terms of both how you can detect enantiomers with optical rotation, for instance, and how you can separate them in a usually a chromatographic technique. And we're going to talk about that toward the end of this chapter. All right. So if you have enantiomers in that first example, it's kind of small, but this is really simple. What you need, the first thing you look for at a carbon is, do you have 4 unique substituents? And in this case, we do. We have hydrogen, chlorine, fluorine, and bromine. So we have the potential for a chiral center there on that carbon. Then you look for their positions. And in the left-hand one, you've got fluorine coming out, bromine going back, chlorine's in plane, and hydrogen's in plane. And in the second one, is it a mirror image? Well, yeah. If you put a mirror down between those two drawings, you'll see that they're reflections of one another. But they're not superimposable, right? You can't just pick one up, slide it over to the side, to the other side, and set it on top of the other one. It won't work. So those are enantiomers. They are isomers of one another, and they have the same connectivity, but you cannot superimpose them. Okay? Mirror images. I already said that. Let's see. Okay, that's a good rule to follow. When you're looking at the mirror image, each of the atoms in the reflection should be the same distance from the mirror. Right, so the ones that are farther away on this side should be farther away on that side. Let's see. So this is the author's idea of simplifying it. I don't know if it does that or not. Okay, this is a case where you want to draw the mirror image of any given molecule. So we start with the carbon, and then the chlorines are going to be in the plane of the paper. So the chlorine has to be drawn close to the mirror. The fluorine, on the other hand, is coming out, and it's probably on the next slide. The fluorine is coming out, but it's the same distance also from the mirror. And then the bromine is going back in both images. It's going back into the paper, but it's the same distance on both sides. And then hydrogen, of course, is in the plane of the paper. So there we've produced the enantiomer for that molecule on the left. We've made that one on the right. It's a mirror image, but it's not superimposable. All right, so chiral refers to hand. Achiral means that a molecule is achiral if it does not have an enantiomer. You cannot produce a mirror image of the molecule. And that usually means two of those substituents around that carbon are identical. They're the same. Two hydrogens, two chlorines, two methyl groups, whatever the case may be. So we're starting off simple, right? These are just one carbon, but it can get complicated, like we can get ring structures too. And we all recognize the one on the right is the chambered nautilus, cut in half. Okay, let's see. Trans 1,2-dichlorocyclopropane is chiral or achiral. We'd have to set up the mirror image, put a mirror in the middle, and see if we can draw a mirror image of that is not superimposable on the original molecule. So we'll take a few minutes and try this one. I'm curious too. So I'm going to draw it like they drew it. This and this is vertical, and then like that. And then we've got chlorine here and a wedge chlorine there. Okay. So here's our mirror. What would this ring look like as a superimposed image? This one would go up like about like this. And that would be vertical. And then that. So that's the mirror image of the ring. Now this one's going to have that chlorine. This one's going to have that chlorine. Okay. Now, is that one superimposable on this one? Well, if we bring it over here, we can't rotate it in any way. I mean, if we take it over here like this and rotate it, then this one is still going to be out and this one's in. Right? So it's not superimposable, is it? Okay. So I'm thinking that this is a chiral molecule. Yep. And the author agrees with me. That's good news. Okay. We could do two different things. We could take it and slide it over here, like this is my hand, slide it over there, not superimposable. But we can't just bring it over here because now the chlorines are in the wrong place. So if we bring it over here and then we rotate it like that, actually, we have to rotate it this way. Right? In order to get the chlorines on the same side of the molecule, we have to bring it over here and rotate it like that. Now this is in, that one's out, this one's out, and that one's in. So it's not superimposable. Hey. Yeah. Oh yeah, sure. Yeah, sorry. No problem. So we have a chiral molecule here. Okay, here's another test for chirality. It's called the plane of symmetry. If the molecule, if we can put a plane anywhere in that molecule and gives us a mirror image on either side, then it's not, it's achiral, it's not chiral. So for this example, we have chlorofluoromethane. Now, instead of drawing it, I think the picture there should explain. See, the plane of symmetry goes through the molecule, and we're picking. You can pick the plane. Right? You could put the plane through the hydrogens, or actually, that wouldn't give us any information. If you put the plane through the carbon and the fluorine and the chlorine, then you've got hydrogens on both sides of that mirror. Right? It's that it has a plane of symmetry through the halogens, which means this molecule is achiral. Sorry. That's okay. One other thing you'll notice is, in this case, there are not 4 unique substituents on that carbon. Right? You've got 2 hydrogens. So the plane of symmetry works for this because you have 2 of the same substituents there. Now let's see, the one on the right, got to get this out of my way. The one on the right, if we draw the same plane through it, now we've got bromine on one side and hydrogen on the other. That's not a plane of symmetry. Plane of symmetry means that you've got the same thing on one side of the plane as you do on the other side. So the second molecule with the bromine, fluorine, chlorine, and hydrogen on it is chiral. It does not have a plane of symmetry. Here's another concept. It's called the chiral center or the stereocenter. So in this case, I think what we're looking at again is, for at least for carbons, is 4 unique substituents, X, Y, Z, and W, X, Y, Z. And that will give you a chiral center. But I'm thinking that there are some molecules that have what appear to be chiral centers, but if you throw in a plane of symmetry, they might not meet that definition, especially for cyclic groups where you have ring structures. That can be a problem and could nullify the chiral center, where you don't have a chiral center with a ring structure. You think you do, but if you apply the plane of symmetry, then it may negate that. Okay. So what are the relationships between these configurations? Well, if we exchange 2 subunits, exchange any 2 subunits attached to a chiral center results in the opposite configuration. And what we're actually saying here, and we'll say it again later, is if you do exchange any 2 of those, you're going to get, wait a minute, is that true? I was about to say that would give you an enantiomer. It would give you an isomer for sure. And in this case, in this example, it does give you enantiomers because they are mirror images, non-superimposable. But I don't know if that's going to hold with more complex molecules. You just swap any 2 of the substituents. Now, if we swap 3 or more, I think that's going to take you back to the parent molecule. If we swap W and X and Y and Z, then it takes you back to the same molecule. But if you swap 2 of them, then that should give you around a chiral center. That should give you an isomer. Now look at B. I mean, the single carbon is easy, but when you get complex multi-carbon structures, you have to look for differences in substituents around the chiral center. And this 3-methylhexane is a good example. Do we have a chiral center in there? Well, let's draw the molecule out. 1, 2, 3, 4, 5, yeah, hexane. 2, 3, 4, 5, 6. And then we've got methyl group there. Okay. If we look at each one of these in order, and we would probably start from this end. Right? Is this a chiral center? Well, how many? It's got 3 hydrogens on it, right? 3 hydrogens in one other group, that's not chiral. These are all the same, 3. Here you've got 2 that are the same. two hydrogens. That's not chiral. That's not chiral. Neither is this one, or this one for the same reason as one. So these are not chiral, but this one might be. So we've got a methyl group here, right? We've got a 1, 2, 3, a propyl group on this end. We've got a hydrogen here that's not shown, and we've got an ethyl group on this end. So that is a chiral center. It's got a different one here, 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 and here. Okay, that can throw you. That's why I'm making the point. Okay. How about trans 1,2-dichlorocyclopropane? Let's see. Does it have, well, does it have two chiral centers? Let me draw it the way they drew it. Like this, this, and this. And then on this number 2, right? And on this number 1, right there. Okay. If we say here, right, is that a chiral center? Well, it's got 1, 2, it's got 2 hydrogens, not probably, it does have 2 hydrogens here. This one has a hydrogen here, and this one has a hydrogen there. So this is not a chiral center. But this one has a hydrogen, chlorine, and then 2 carbons on this side, and only 1 carbon this direction. Right? So that's a chiral center, and that one, by the same reasoning, is a chiral center. We have 2 chiral centers here. Now, is the molecule itself chiral? We look for a plane of symmetry. Right? So if we draw a plane of symmetry here or here, no, because this is pointing in and this one's pointing out, depending on which plane you're looking at. But what other plane have we not brought up? Is it on the next slide? Divide the ring in half. Well, we've done that. Those are not planes of symmetry. Oh, it conveniently skipped over this plane right here. Right? But is that a plane of symmetry? No, because this one's going in and that one's coming out. That's a major difference. So this molecule is chiral. It has 2 chiral centers. Now we're going to learn eventually the IUPAC way of identifying the arrangements around chiral centers. That's coming. Okay, how about this one? Chiral centers other than carbons. Well, this is a tertiary ammonium compound. Right? It's like ammonium, NH4 plus, only we substitute others in there for hydrogens. And we've got a methyl, we've got C5H5, that's a phenyl group, and we've got an ethyl group, and we've got a propyl group. Those are all different around that nitrogen. Nitrogen, in this case, is a chiral center, quaternary ammonium ion. And this is probably something that you could use in a cleaning compound. If you read labels, you'll see that some of them are quaternary ammonium compounds. They are as effective as ammonia. They're just not as noxious. Okay. Oh, one strict rule. Molecule that has exactly 1 chiral center must be chiral. All right. I'll agree with that. Okay. But If there are two chiral centers, you have the possibility for what's called a meso compound. And what we mean by meso is even though you've got chiral centers, the molecule itself is not chiral. Okay, this molecule on the left is the one that we looked at before. Since the chlorines are trans to each other, you don't have a plane of symmetry. So this molecule is chiral. But if they are cis to one another, and you put a plane of symmetry, there it is. I knew they were going to come up with it. If you put that plane of symmetry between the chlorines, you have mirror images across that plane of symmetry. This molecule is achiral, and it's called meso because it has two chiral centers and a plane of symmetry. That plane of symmetry means that this molecule will not be chiral. Okay, so this should be simple. Which one of these is meso? A. It has that plane of symmetry. Yep. A is meso. Okay. Absolute stereochemical configurations. Oh, this is what I was talking about. This is the Kahn-Ingold Prelog rules for assigning configurations to a chiral center. And you have to do this for every chiral center in the molecule. So some of them can be monsters. If you ever look up, out of curiosity, if you ever look up a large molecule in, say, Google it, and you go to whatever is available, sometimes you can do Wikipedia is okay, but usually I go to the ACS websites. Anyway, you can see these long names, and they have S's and R's in them. And that just tells you the nature of the chiral center. So for this example on the left, the only two chiral centers we have in this molecule are the second and the third carbon. If there's an R configuration around the third and an S configuration around the second. And if we swap places with those chlorines, we just swap the configuration. So now the third chlorine is S and the second chlorine is R. And we identify those at the beginning of the molecule in parentheses saying which carbons are chiral and what's the nature of their chirality. So 2 is an S and 3 is an R. Now I'm going to give you the rules for determining that in just a second. Right? I told you it was going to get more complicated. So here's the Kahn-Ingold Prelog, the SIP system. And it has to do with finding the chiral center first, focus on one at a time. Then you have to establish priorities, 1 through 4, because there are only 4 groups around that carbon. So you establish the priorities, and you put the lowest priority in the back. Very often that one will be hydrogen. Hydrogen is the lowest priority of anything if it's there. And then you identify the priorities, right? Based upon rules that you're going to get in a minute. In fact, I think that handout has priorities. Yeah, those are good. Those are priorities. And then you go from lowest to highest priority with the of the 3 remaining, right? The very lowest is pointing in the back. And then you take the other 3 and go from lowest to highest. And what direction is it going? If it goes to the right, that's Latin is rectus, which means to the right. And if it goes to the left, that's sinister. That goes to the left. I always find it easy to remember those because the political left in this country is sinister. in their tactics. So left is sinister, is S, and right is rectus for R. Okay. Okay, we need to assign substituent priorities based upon the atoms at the point of attachment. Right. Scratch what I said earlier. These are different priorities. I'm sorry. Those are nomenclature priorities. The Coningo-Prelog priorities are based upon atomic number. So the highest priority is the highest atomic number for the immediate attached substituent. So if you had these four groups around this carbon, and you had a hydrogen here, and let's say you have a chlorine here, and you have a fluorine here, and you have a bromine here. Actually, this would have to go back also. There, we do it like that. Okay. So what are the priorities here? Well, this is the lowest priority. The highest priority would be the highest atomic number, which would be bromine, correct? So that would be 1, this would be 2, and this would be 3. Now what we do is we tilt the molecule to put hydrogen in the back, and then we go 1, 2, 3. This is S. Sinister. Now that's an easy one because there's only one chiral center and there's one atom attached at each point. If you have the same atom attached here, say we have a carbon here and a carbon here, well, that's not chiral. Let's suppose instead we have a methyl group here and we have an oxygen here. So the next attached point is oxygen, right? Oxygen has a larger atomic number than carbon. So now this one becomes the highest. This one is the highest priority. This is the second one. This is the third one. So now this molecule would be 1, 2, 3. This would be rectus. Go to the right. Okay. So if you meet a tie, then you go to the next attached atom. Let's see. There's probably more coming. Okay. So in this example, you have that chiral center with the chlorine and the hydrogen, and you've got carbons attached to each side. Then you go to the next one. Carbons again. Exact the same carbons. Then you go to the next one. Chlorine beats carbon. All right. So the chlorine is the highest priority, and then the carbon side of the chain with chlorine on it is the next priority. So this one would be rectus. Go to the right. Okay, let's see if I got that right. Yeah. So this would go to the right. Let's see. What if you have double or triple bonds? Okay, so an atom that's has a double bond to another atom is treated as having 2 single bonds to the atom. And if it's triple bonded, it's treated as having 3. So, for instance, if you have that attached group, that ethene group attached in A, then you treat it as if you've got a carbon attached to another carbon with a carbon each on those carbons. Or if you have an NH, then you have the another N and another carbon attached to each of the carbons in the nitrogens. So it looks like it's like cross multiplying. If you have a double bond, if you have the carbonyl group on the far right, then you put an oxygen on the carbon close to the connection point, and you put another carbon on the oxygen. For the purposes, this is not actually bonds, but for the purposes of priorities. Okay, how does that affect our an example? Okay, so here we have a chiral center, 3-methylhexanone, with a methyl group on one side, a hydrogen, and then we have a propyl group on the left, and we have a vinyl group on the right. That's what that's called. Vinyl is an attached group that's double bonded carbons. So we would rewrite it as if we put one of the carbons on the first carbon and the other carbon on the second carbon, and then we establish our priorities. And then we look at that second, then we look at the carbon. So I'm not sure if I'm explaining myself very well. What's attached to those first carbons, right? We've got a carbon, we've got a hydrogen and 3 carbons. But since there's a double bond on one of them, now we're going to assess the priority based upon the attachments to that first carbon. So the one on the right with the double bond now is assessed as 2 carbons and a hydrogen. Right? So it's the carbon attached, the extra carbon, and the hydrogen. And then we look at the one on the left. That one is assessed as a carbon and 2 hydrogens. So it's lower priority. And then the carbon, the methyl group, is assessed as 3 hydrogens. Right. So, okay, I didn't explain that right. Let me put it on the board. 1, 2, 3, 4, 5, 6. Yep. 3, 4, 5, 6, like that. Okay, so we've got a methyl group out here. We've got 2 hydrogens there. We've got 2 hydrogens here. We've got a carbon here. We have a hydrogen there and a methyl group here. Okay. And then we had a hydrogen here and a double bond to a CH2 here. Yeah, okay. So we're going to take that double bond, and that puts, for our purposes, a carbon here and another carbon here. Okay, so when we assess, this one has how many, what is attached to this carbon? Well, it had a hydrogen, and a hydrogen attached to that carbon. This carbon has attached to it a carbon, and a hydrogen. Okay, so we're not counting this carbon, we're counting what's attached to it, because we've got carbons attached on all sides. This one has a carbon and 2 hydrogens. Okay, are we clear so far? All right. So now the priority, this hydrogen is a 4. This one is a CCH, so this one is the highest priority. This one is a CHH, that one's 2, and this one's 3. So with hydrogen in the back, we go 1, 2, 3. This is sinister. Okay. What happens when the 4th priority substituent does not point, does not point away? Oh, when the fourth, the very lowest priority, is not pointing away from you. Okay. If it points toward you, the simplest way, say if this hydrogen pointed toward us and that methyl group was back, you would still do the priorities. You would do the priorities, and then you would invert it. So if this methyl were actually going to the back and the hydrogen came out the front, we would just leave it like it is, do the priorities, say under those circumstances it's S, but now we would reverse it, and it's actually R. That's the easiest way to keep from making a mistake. Okay, I think that's what we're doing in this example, so I'm not going to stop here. All right. Mirror images that rapidly interconvert, single bond rotations and nitrogen inversion. If a molecule and its mirror image rapidly interconvert, then the molecule is effectively achiral. Okay, now we're looking at conformers. Oh, you can get mirror images of a conformer, but this molecule is spinning around that sigma bond. So it can't be chiral because it's not fixed in space. And what's more, none of those carbons has 4 unique substituents. So that's a dead giveaway there. I don't know why we're wasting time on this one. What about interconversion by chair flip? Well, just because you flip it, well, for example, that the image on the left, if we flip that chair, it's now superimposable, right? It's definitely not chiral. Yeah. If you flip the chair and you can still superimpose them, then you don't have a, oh, I see what's happening. Okay. For the one on the right, you can flip it and it looks different, but it can flip back just as easily. Right. So neither one of those are, the chair flip does not introduce chirality. That's the point. That's the takeaway from this slide. How about Haworth projections? You're going to run into those. They're particularly useful for determining chirality of cyclic molecules because they simplify that chair conformation. The chair is useful in some instances when you're looking at steric hindrance, for instance. But if you're focused on chirality, then the Haworth projection is probably more useful. You have a plane of symmetry for the cis molecule, that one on the left. But you don't have a plane of symmetry for the trans molecule. So the trans molecule should be chiral and the cis molecule is not. How about nitrogen interconversions? In this example, N-methyl ethylamine. So that's a naming convention we haven't covered yet. If nitrogen is the central atom, then where are you, if you say it's a methyl ethanamine, where does the methyl go? Or if you said, yeah, that's a good example. If you put an N in front of the substituent, that means that it's attached to the nitrogen. And this goes for more complex molecules also. N-methyl ethanamine. Okay. So, and we can draw these two species, right? And they're obviously mirror images of each other, but are they superimposable? Well, all you have to do is rotate the molecule around and see what happens. If we rotate it around so that well, if we slide it over, of course, it's not superimposable. But if we flip it over, then what the wedge methyl group on the left is trying to superimpose over a dash methyl group from the red one, right? If you just flip it over, then everything is reversed, except for the hydrogen because it's in the same plane. But you don't have superimposable images. And this particular molecule, these two molecules are enantiomers of each other, simply because they're not superimposable. Now, what's the point of this one? If we look at the orbitals, all right, where is that double bond? I mean, excuse me, that lone pair. All right, we've got a sp3 hybridized nitrogen atom is required for that lone pair. Oh, I see what's happening. We're flipping back and forth. If it's like an umbrella turning inside out in a strong wind, right? So you got an umbrella on the left-hand side and it's inverted on the right-hand side. And for this to happen, nitrogen must transition through an sp2 hybridized atom in order to get to the other side where it's sp3 hybridized again. But what does that tell us? If it does that, then it's got those two molecules like on the previous slide, right? We've got non-superimposable mirror images, but they can easily flip back and forth. I wonder if this nitrogen inversion means that the molecule is not chiral. Yeah, if it undergoes inversion, then it's not chiral because it can easily flip back and forth. Yeah, okay. So scratch that earlier statement. It's not chiral. This flip, this umbrella flip, happens in equilibrium with the other umbrella. So that's one case where it looks chiral, but it's not. Okay, how about diastereomers? All right, diastereomers are those molecules that are not mirror images of one another. And the example here is cis versus trans 1,2-dichloroethene. They have the same formula and the same connectivity, but they are different molecules. Now, how do we deal with them? Well, the old way was to say cis and trans. If you had something like this, and you put a chlorine here and a chlorine here, that's trans. If you have this one and you put a chlorine here and a chlorine here, that's cis. But in all circumstances, the cis and trans don't always work. So we came up with this alternate IUPAC sanctioned version. And if the higher priority groups are on the same side of the molecule, then they're Z. This is the Z isomer. If they're on the opposite sides, this is the E isomer. Now, those are the first letters of German words. that refer to, let's see, are they going to tell us the Z configuration, E configuration? Oh, no, come on. I'm trying to remember what they stand for. I think Z stands for Zusammen, which means same side. And E stands for some other German word that I can't remember right now, which means the opposite side. The easiest way to remember them is Z is the same side. Just introduce a German accent. And then E is the opposite. Yeah, that works for me. But you've got to have the highest priorities identified, and then what side of the double bond are they on? Now, would that work for triple bonds? Nope, not where carbon's involved, because those molecules are linear, right? sp hybridized triple bond molecules are linear. You don't have this option. But for double bonds, bonded carbons, then you look for the priority. And this is the same priority rules that you would use for, that we used for the Kahn-Ingold-Prelog system. Let's see. Okay. With this one caveat, notice that we're looking for priorities on the particular carbon. So that chlorine on the left is a higher priority than the carbon on the left. And on the right, the carbon in the methyl group is a higher priority than the hydrogen. We don't mix them. I mean, there's a boundary but on the double bond, and we only want the priorities for the two attached groups on the carbon. Okay? All right. Believe it or not, you can have diastereomers with no double bonds if you have ring structures. So how do we tell a diastereomer? If we have two chiral centers, in this case, around the first and the third carbon, we have two chiral centers, and we determine their S and R prefixes. Then if you have a non-reversible prefix, in this case, S and R, if you could reverse them to say R and S, then you don't have a diastereomer, you have an enantiomer. But if you can change one of them, right, S and R, you can change it to S and S, then you do have a diastereomer. But if you can reverse both of them, then you can draw the enantiomer. Okay. 1-chloro-2,3-dimethyl cyclopentane. Draw its diastereomer. I think the easiest way to draw the diastereomer, well, you have to find out, excuse me, you must determine the chiral centers first. Right? So let's do that. Find the chiral centers. Who's got the chiral centers? This is a 5-membered ring. And let's see, here and down here like that. Okay, so we've got chlorine here, we've got a methyl here, and we've got a methyl here. Okay. So these are obviously not chiral centers here. How about this one? Potentially. So let's say we go from here, that's different, and that's different. We got 1, 2, and then 3, 4 here. This way we got 1, 2, 3, 4 there. I think this is a chiral center. How about this one? If we go here, 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 and here, versus here, 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 and here, I think that's a chiral center. How about this one? Well, this one has 1, 2, 3, and there's a hydrogen there. Well, there are hydrogens here also. All right, is this a chiral center? Well, go this way. We got these 2 carbons with methyl groups on them, and this way we've got 2 with no methyl groups. It looks like we've got 3 chiral centers there. How many chiral centers are there? Okay. Okay, got that right. To draw a diastereomer, how many chiral centers should have their configurations reversed? You can reverse, I think you can reverse 2 of them, but not all 3. If you reverse all 3, then you've got an enantiomer. But if you reverse 1 or 2, then you can get a diastereomer. Right? So these are your possible diastereomers. Okay. We've on the left one, we've reversed the top methyl only. And in the right one, we've reversed the top methyl and the side methyl. So those are 2 diastereomers of this molecule. All right. They didn't ask us to do the RNS on this one, did they? No. Okay. Let's see. I was looking at something earlier. Everybody got a copy of that sample exam? Yeah. Okay, good. Or did we run out? Yeah, it is there. But it doesn't have answers to it. So take a look at that, and the ones that you can't figure out, bring them to class, and we'll talk about those. All right. All right. So here's a quick way to determine how many isomers can be produced based upon the number of chiral centers. You have to determine the number of chiral centers first. Now, this doesn't mean that all of the isomers are going to be chiral, but this is the maximum number of isomers that can exist for a molecule with n chiral centers. 2 to the n is the maximum. You can't have any more than that. And then you have to determine which have planes of symmetry. And those that have planes of symmetry, you throw them out. They're not chiral anymore. Okay. Oh, here we got some steps. Okay. Identify all the chiral centers. That's the first step. Draw the first structure by specifying the configuration at every chiral center. Use dash wedge notation for the first structure. The choice of configurations doesn't matter. Okay. Draw the second structure by reversing the configuration of only 1 chiral center. Draw the next 2 structures by reversing the configuration at chiral center 2. Yeah, it's an exponential geometric progression, right? Each time you add a chiral center, you've doubled the complexity. So when you get to the next 4 structures, you reverse the configuration at chiral center 3. So you're doubling as you go. And then right, this is brute force. You create all the possibilities, and then you start axing out the ones that don't satisfy. So here's an example, 2,3-dibromo-4-methylhexane. We've identified 3 chiral centers, right? Does that make sense? Yeah, that looks reasonable. We got 3 chiral centers there. So I have 8 possible isomers, right? So 1, 2, 3, 4, 5, 6, 7, 8. So step 1 is we drew one with all the groups pointing toward us. Then the first one we changed that bromine. And then we go back and we flip those 2, and then we make both of them back into the page. So that gives us 2 more. Then we take, let's see, how are we going to E? Okay, we're going to E by taking the 3rd carbon, and we're putting that methyl group backwards. And then we're keeping that one backwards, and we're sending the bromine backwards. And then if we keep that one backwards and send them all 3 backwards, we get the lower right-hand corner. But if instead we bring the left-hand bromine backwards and keep the methyl group backwards, then we keep the middle bromine forward. So that gives us our other 4. So that, and we count them up, 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 possibles. Now we have to go in and determine, do we have any redundancies here? Well, it doesn't say. Okay, well, let's just look at them. A and B, those are diastereomers, right? They're not mirror images of each other. How about C? C is a diastereomer of the first one and the second one. So do we have any mirror images in there that are not superimposable? How about A and H? Right? All 3 back, all 3 forward. That's for another day. I'm taking up too much time. If I keep going like this, we're not going to have time to even look at the yeah, we got 22 minutes. Right. Okay, Fisher projections. We did Howard. Now Fisher. Okay. Let's see. Oh, that's right. We got till Saturday to do exam 2. All right, so when we come to class Wednesday, we're going to look at chapter 6, arrow pushing, and do the lab. Okay, yeah, I'm orienting myself. Fisher projections. Okay, there's a man by the name of Emil Fisher who was working with, let's see, I think this was in the beginning of the 20th century. He was working with sugars, and he got tired of drawing the dash wedge. Right? He wanted a simple way to draw these molecules in such a way that he could do it quickly and reliably. So he invented this projection that is like a bow tie. It's like a little man with a bow tie. Right? So his arms are like this. And his torso and neck are like that. What that means is when you have a molecule that has several substituents on it, then you can draw it like this. So we could put maybe hydrogen here, chlorine there. This is not going to be a sugar molecule. You can put a fluorine here and you can put a bromine there. So the bromine and the chlorines are coming out of the board, and the hydrogen and the fluorine going into the board. And that's the way we would represent this. Draw across there, 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 there. That's what it means. This means that. Okay. It's really simple for single carbon molecules. It gets more complex as you add carbons. And Lee has got an excellent video on this one also. We don't have time to look at it, but there's a link in Brightspace for it. So the important thing here is if you want to produce a change in stereochemistry for this molecule, all you have to do is swap any two of these. You could swap these two, you could swap these two, swap those two, and you'd have a different isomer. And if you swap the correct ones, say if you swapped, let's see. Well, if you rotated this, then you would effectively be swapping. Because now, if you rotate that, these are going in and these are coming out. But that doesn't give you a new molecule. Why? Because if you rotated this to change that configuration, all you have to do is flip it over and it's the same molecule. So rotating gives you the same molecule. And I just told a fib. We rotate it 90 degrees in the plane of the page. That gives you an opposite stereochemical configuration. Let me see if that works. Rotate it 90 degrees. Now hydrogen's here, fluorine's there, and bromine's there. All right, what would that look like up here? That would be carbon here. That would be hydrogen, fluorine, bromine, and chlorine. So if we, yeah, that's right. Because if we rotate this like that to put the fluorine on top of the fluorine and the chlorine and everything in the right position, now, instead of out, this goes in. Okay, so rotating at 90 degrees does give you a change in stereochemistry. Okay. These are sugars. What type of sugars are these? These are aldoses. Right? Because they have a carbonyl with a hydrogen on the end. They're aldehydes. So if we look at the way this is arranged, for the D-allose, all of the hydroxyls and the hydrogens are coming out at us. Whereas the D-glucose, the second chiral center, right, the top aldehyde part and the bottom CH2OH, those are not chiral. But each of those crosses in the middle are chiral, every one of them. 1, 2, 3, 4. You got 4 chiral centers in this molecule. And all we did was flip hydroxyl on the third carbon from the top. So D-glucose and D-allose are diastereomers. But if we flip everything from D-glucose and put the hydroxyls on the right and the hydrogens on the left, opposite one another, now we have an enantiomer, L-glucose instead of D-glucose. And that's probably the main reason that Fisher wanted to use this, because it was so easy to tell the difference between the two, to tell if you've got an enantiomer or a diastereomer. Okay. So if the if we want to determine the R and S for each one of these, right? D and L is an old configuration. It's an old sort of grandfathered in. And it has to do with the rotation of polarized light. D stands for dextrorotary, which is the polarized light is rotated to the right, and levorotary is to the left. Okay. But what does that mean in terms of R and S? Well, sometimes D means R and sometimes it means S, right? So there's no direct correlation there. You have to work it out. So in this case, we have hydrogen is pointing out, right, in that molecule. So if we do the sinister to the left, from oxygen to carbon to well, the carbon with the carbonyl is a higher priority than the alcohol group. So we go one, and oxygen direct 1, 2, 3 to the left. But since hydrogen's pointing forward, we have to reverse it. So sinister to the left, this is actually an R configuration. Now, how would we do that for each one of these? Well, once we convert to a Fisher projection, and this is where I would advise you to watch Leah's video on converting dash wedge to Fisher projections. Because if you just look at that and try to visualize it in terms of the Fisher projection, you got a 50-50 chance of getting it wrong. Now, of course, the number 1 carbon doesn't matter, but the 2, 3, 4 are chiral centers. And if we flip it on its side, that doesn't tell us exactly what we need to know, because those bonds between the carbons are, some of them are in and some of them are out. So this is the author's idea of converting a zigzag to a Fisher. So rotate 90 degrees in the plane of the page. All right. And that puts that's not making a lot of sense. I would suggest that you look at Leah's description. I think it'll make a whole lot more sense. If I try to explain it using this slide, it's going to confuse you. So watch the video with Leah doing it. Now, if we look at what happened in the process of conversion, right? This would be toward us, toward us, toward us. So that's not a direct conversion, because the number 4 OH is back, and in the Fisher it's forward. Right? So it's not a direct one-to-one conversion. And then she'll also explain how to convert from Fisher back to zigzag with dash wedge. Okay. All right. How about physical and chemical properties of these isomers? I've got 10 minutes to talk about it. How many more slides do I have? Too many? Okay. Um, Constitutional isomers always have different physical and chemical properties. That is, they're not, their connectivity determines that they don't have the same properties, physical or chemical. Notice that with pent-1-ene versus trans-pent-2-ene, you got a movement of the position of the double bond. That affects how it reacts. That affects how it behaves physically. Obviously, the constitutional isomers of but3-ene-1-ol versus tetrahydrofuran, they're definitely different in terms of, the example here is boiling point. But if you have enantiomers, their physical properties are exactly the same. The boiling point for these two enantiomers is exactly the same. Now, we've only talked about physical properties here, but the chemical properties are a little, it's difficult to wrap your head around enantiomers. Their chemical properties are the same in one environment and different in another environment. And the other environment is the one that we have to pick so that we can separate them, right? Remember, let's see, what is it? The thalidomide back in the 40s and 50s, pregnant women were given thalidomide to alleviate their morning sickness. Okay. They found out too late that it caused birth defects. Thalidomide. Oh, that's something else. Yeah. Thalidomide comes in two enantiomers. So when the chemists were producing the drug, they didn't separate one enantiomer from the other. One enantiomer does not cause birth defects, and the other one does. And they were delivering the mixture. Right? We found that out too late. So let's see. We've talked about this before. So achiral environments. Oh, no, we didn't. Okay, so in an achiral environment, enantiomers have exactly the same physical and chemical properties. In a chiral environment, enantiomers have different physical and chemical properties. And we use that fact to separate them, particularly with chromatography. So how would you change the environment from achiral to chiral? If your stationary phase in the chromatography column were achiral, then you couldn't separate them. But if you had a stationary phase that was chiral, is only one enantiomer of the stationary phase, then you could separate chiral compound mixtures. Diastereomers, of course, they have different physical and chemical properties. They're examples. The first separation of enantiomers was done by Louis Pasteur. He was investigating the compound sodium ammonium tartrate. And he saw that there was a difference in the crystals that he isolated from the reaction. So he used a microscope and he painstakingly separated those crystals by their shapes, their appearance, and found out that they had exact opposite optical rotation. That was the first identification of enantiomers. I think those are enantiomers. Yes. So one way to separate enantiomers is to convert them temporarily into diastereomers. And those are easy to separate. And then usually you attach a side group that changes the molecules into diastereomers. Then you separate them with by some physical means, and then you remove you regenerate the enantiomers by removing the component that you added originally. Optical activity is simply plain polarized light. Everybody's had sunglasses that are polarized. For most of the road glare that you get when you're driving comes off of the road or other vehicles in this plane. So you just have the lenses, the Polaroid lenses, rotate the other direction, and it blocks out that glare. All right. So the degree, the angle of rotation, the amount of rotation depends on the actual length of the tube. It's like Beer's law, right? The longer the light path, the more it absorbs. Well, the longer the light path, the more it rotates. And if you have a mixture, if you have a mixture 50-50 of both of the chiral compounds, then you're going to get a zero angle of rotation. But if you enrich in one of them, the more you have of one, the more it's going to rotate in favor of that one in the direction it goes. And if you have pure compounds, pure enantiomers, then and the same path length, they're going to rotate exact opposite angles. Want to go an angle this way, the same angle the other way for the other one. And there's the formula. Specific rotation, that's characteristic of the chiral compound. And there's the path length, L, and C is the concentration. So if you increase the concentration of one over the other, then you're also going to get a change in the angle of rotation of plain polarized light. That's the term I was trying to think of. A racemic mixture. That's what that thalidomide was. It was a racemic mixture. It had equal amounts of levorotary and dextrorotary compounds. Oh, there it is. There's thalidomide. The one on the right causes birth defects. The one on the left alleviates nausea. They're enantiomers of each other. I guess in those days, they either didn't recognize that there was a difference or they didn't have the technology to separate them. And the drug company had put so much money into research, they got to recoup some of their money. So they said, I don't even know if it was determined whether they knew there was a problem in the beginning. Maybe they didn't know. Okay, we're going to skip that. The DNL system, I said this earlier, it references optical rotation. And it's based upon glyceraldehyde. Glyceraldehyde is the very simplest. It's a one carbon molecule. Okay, there's glyceraldehyde. And that's the D isomer, and the L isomer is in the bottom. And they, and for your, for more complicated, more carbons, okay, I'm out of time. More carbons in your molecule, we look to the one that's closest to the C2OH. Excuse me. No. It's the one closest to the carbonyl group. Carbonyl group is the D versus L end of the molecule. The problem with that is if you've got other chiral centers in there, then the D and the L doesn't tell the whole story. All right, you can say that for amino acids, you can say it for sugars. All right, and we're done.